let's do this formality and go through the entire curriculum, states of matter. Now you do know the definition of particle separation. Now let's talk about solids. How do you visualize solids? Let's talk about the kinetic particle theory. So I have written a lot of things because I did not want to. That is what we are discussing now, the absolute zero, and then what happens at absolute zero in degrees Celsius, in Kelvin, the interconversion. So just to give you a fair idea of the temperature scales, because we need to know them before the next class. Hello students, welcome to your own physics class. Students, it's been a long time we are learning about motion, forces and all these things, energy. Today we are going to start with a new unit of thermal physics. In a way, it's going to bring a little freshness to our learning of physics, because it was, mostly about motion and the related parameters that we were talking about. Though we cannot exclude motion even from this branch of physics, but still there will be a lot of new parameters that you all are going to learn, and I hope you will enjoy learning all these things with us. I will try to repeat all the concepts at least twice during these videos so that the concepts are really thorough and they are really into your head. Alright students, so now without wasting any time, let's start with the new unit of physics, that is thermal physics. Alright. So first, just let's do this formality and go through the entire curriculum, the expectations, that the concepts that you need to know. So what are we learning? Kinetic particle model of atom, states of matter. So if you have chemistry, you might have learned these concepts in your chemistry also. So in a way, you can always compare what you have learned in chemistry, but the concepts are still the same. Maybe there will be a few more concepts that you're going to learn. So know the distinguishing properties of solids, liquids and gases. Know the terms for the changes in state between solid, liquid and gases. So of course the three states of matter and their interconversion. Alright. Then particle model. Describe the particle structures of solids, liquids and gases in terms of the arrangement, separation and motion of the particles, and represent these states using simple particle diagrams. I am just reading it out to you. Don't worry if you are not able to correlate with the things, because that is what we are going to learn. Describe the relationship between the motion of particles and temperature, including the idea that there is a lowest possible temperature known as absolute zero. This is very important, student, very recently added to the syllabus. Let's be very thorough and particular about this. Alright, where the particles have least kinetic energy. Alright, describe the pressure and the changes in pressure of a gas in terms of motion of its particle and their collision with the surface. All this we are going to talk about. Know that the random motion of microscopic particles in a suspension is evidence for the kinetic particle model of matter. Alright, describe and explain this motion, sometimes also known as the Brownian motion. We'll talk about it in terms of random collision between the microscopic particles in a suspension and the particles of the gas or liquid. So I have just read it out to you. This is the core syllabus. Now let me tell you what extra do you need to know, the supplement syllabus. Okay, let's read it out together. Know that the forces and distances between particles and the motion of the particle affects the properties of solids, liquids and gases. Describe the pressure and changes in pressure of a gas in terms of force exerted by particles colliding with surface, creating a force per unit area. So somewhat what we have already talked about. Know that microscopic particles may be moved by collision with light, fast moving molecules, and correctly use the terms atoms or molecules at distinct forms from microscopic particles, right? So atoms and molecules and microscopic particles. So what is the difference? We will talk about, right? That as well. So that's the curriculum, students. I hope you are now having a clear-cut idea what all things we are going to learn in this particular video today. Alright, so I think we can start now. Alright, so okay, so yeah, so all this we have already talked about, knowing the temperature. So this is all discussed already, so I think we can skip this part and move on to the next slide. Alright, so states of matter. Now you do know the definition of matter. You have learnt it from so many previous classes now. Anything that occupies space and has mass is called matter, right? In a way, I can just give you a clear idea what is not matter. Let's say light. So there is a light bulb in your room. So that light bulb can be classified as matter, but the light that it is emitting is not matter. So matter is something which has a rest mass, right? It will occupy some space. That is what we define as matter. So anything that occupies space and has mass is matter. Matter is made up of tiny particles. Of course, we know that anything, you and me, everything is composed of tiny particles. We are all collection of tiny particles, right? We call them atoms, we call them molecules. So that is what we are comprising of. Okay, and what are the three states of matter? How do you look at that? So one is solid, then there is liquid, and then there is gases, right? And I have just given you an example of H2O. So let's say H2O, I won't call it as water, I'm just calling it the chemical formula H2O. And H2O, the three versions you can clearly see. Of course, this is ice, that is solid, and then this is water, that is liquid, and ultimately it is steam, that is a gaseous form or a gaseous form. Students, so don't understand that the three states of matter are like something is a solid, something is a liquid, or something is a gas. No, something is a solid, it can convert to liquid version as well, and it can convert to a gaseous version as well. So these are interconvertible. There is nothing like this substance has to be solid. It can be liquid also, it can be gaseous also, depending on the situation in which it is in. All right, students, so I hope I'm not taking much of your time on this because this is something you know. Let's talk about the molecular structure, the particle structure in each of them. All right, so you can just make a note. Again, reminding you, just keep making short notes while you're watching these videos. Of course, that will keep you more engaged in these videos. Otherwise, sometimes it can get boring, right? So let's not do that. Okay, so particle separation. Now let's talk about solids. How do you visualize solids? So of course, solids is a situation where the particles are very closely packed, right? They cannot move in bulk. The only thing that they can do is, they can vibrate a little. So just like you might be sitting in your classroom, and while the class is happening, you all are fixed to your positions. All you can do is you can do a hand movement, right? So it is like that. So the fixed position is still there. You can slightly move on your chair. That is how you can visualize solids. The particle in a solid are packed closely together. Now what causes them to pack together is the intermolecular forces. We also call them as bonds, right? So those bonds, they are really strong. The particles are really attracting each other with a very strong force, right? So that is why the particles in a way acquire a regular arrangement, and there is a term for that called lattice. So many times in solids we talk about a term called lattice. Okay, students, this is something I do have an idea that you know already. So not able to move freely but simply vibrate in their fixed position. So the particles cannot move freely. Of course, they can only vibrate about their fixed position. Now what about liquid, students? So how do liquids differ from solids? So again, let me remind you, in liquids also the particles are in a way holding each other up. In solids it might be a very strong bond. So in liquids it might be a little weaker bond, right? It might be a little moderate force, we can call it like that. Sorry. So if it is a strong force in solids, in liquids it can be a moderate kind of a force. Okay, so they are less closely packed. Okay, less closely packed. So what can happen is at least they can move past each other, right? They can slide, they can glide over each other. So in an irregular arrangement, so because it can happen, the particles can slide over one another. They don't have a regular arrangement, right, students? You can correlate. We can't see them. We can't see what is happening at the molecular level, but we are trying to now understand that what it should be like. Okay, able to move around past each other. That's liquids for you. Now let's talk about gases. So gases, of course, how they are very different from each other. the molecules hold their individuality. Like they are not binding with any other molecule or atom, and in a way they can move very freely, right? So there are almost no forces, no intermolecular forces, almost negligible between the molecules. What does that do? That creates a huge difference in the molecular arrangement of solids, liquids as compared to gases. What is that? They can acquire any volume. They don't have a fixed volume. So imagine you have some gas in a box and you open the box and the whole gas will spread out throughout the room. So that means there is no fixed volume that the molecules will acquire, the gas will acquire. It does not have a fixed volume. Okay, so the particles in a gas are spread very far apart compared to solids and liquids. Of course, you know it, students, but you should always, still retrospect what you have learned, and because this is going to form the fundamental of the entire unit. Okay, arranged totally irregular fashion and able to move randomly. So they are not bound with one another and they can move separately. In each molecule can move separately, while in liquids what normally you see is they are always together, right? So there is a moderate force that is attracting them, or you can call it very strong force for solids and strong for liquids, okay? Or you can call it strong for solids then moderate for liquids. The idea is just to always compare the two, that in liquids the force is slightly weaker as compared to solids, right students? I think you should make a note of it and then we move forward. Alright students, so without wasting your time, properties of three states, just let's have this exercise being done. Okay, so volume, of course solids have a fixed volume, they don't change their volume, liquids also don't change their volume, but gases, the volume is not fixed. They acquire the volume of the container they are in, while liquids acquire the shape of the container they are in. So liquids don't have a fixed shape, right? That is what we have written here. So now they are a little flexible, at least they can change their shape. Solids are very rigid, they don't want to change anything, right? And compressibility, so what about solids? So of course they can't be compressed. I have written slightly compressible for liquids. So if you apply a lot of pressure, you can slightly bring the particles even closer in liquids. So they are slightly compressible but not much. So for example, if you have 1 liter of water, it will remain 1 liter only. If you only slightly compress it, it can become like 998 ml, 999 ml. So you can change the volume a little bit. That is why I have written that slightly compressible. And of course gases, there is enormous scope. You can collect the entire air of your classroom and fix it in your fist. So it is like you can compress it to a great extent. What does that tell you about the density, students? So we have learned the concept of density. Of course, what you see here, the more particles in lesser volume, more concentrated. So if you talk about density, of course solids will tend to have greater density as compared to liquid and then gas, though there can be sometimes an exception to that. For example, mercury, where mercury, the particles are in liquid state are quite heavy, right? So there the density can even go past, let's say, iron. So that is the case, but let's not discuss that for now. So let's just talk about how and what things can change. So density, so of course for solid it is fixed again, because mass is fixed. Mass is fixed for all. This volume can slightly change. So density can slightly change sometimes, right? Slightly change and can change tremendously, right students? That's about the density also. I just wanted you to fill all this up. So I hope you can understand now. So yeah, so that is about the three properties, like the three states and their properties. And let's move forward again without wasting time. I think these are the concepts where you can just watch the video and you know them and you don't need to revise them again and again, but this is going to build up your concepts for the further units. All right. So use the properties of the objects learned so far to explain why a gold ring is a solid. So can we write it has a fixed shape? So since it has a fixed shape, no one else classifies for that. So gold ring has a fixed shape, no one else would classify for that because liquids will not have a fixed shape. Milk is a liquid, so it might have a fixed volume, but so you put it in any container, the amount of milk, the volume of milk is not going to change. So fixed volume, but what is going to change? But no fixed shape. So that is how it is not a gas and not a solid, because it has a fixed volume, so it can't be a gas. Okay, air is a gas, so how do we explain that? No fixed volume. No fixed volume, isn't it, students? I hope you're able to understand, and let's move forward. Okay, all right. So now let's talk about the kinetic particle theory. So I have written a lot of things because I did not want to miss on anything, any point whatsoever. So kinetic word, students, let's talk about that. What is kinetic? Kinetic energy, anything related with motion, right? So what are we discussing now? Now we are not talking about volume and shape and all these things. Now we are talking about how the particles are moving, right? As I just discussed that in solids, they are only vibrating. Yeah, so a theory which accounts for the bulk properties of different states of matter in terms of the movement of the particles. So what are we discussing? Movement of the particles. And when we say particles, we talk about the most fundamental particle, which is normally an atom or a molecule. The theory explains what happens during the change of state. So this is what we are discussing, change of state. Okay, when substances are heated, the particles absorb thermal energy, which is converted into kinetic energy. This is the basis of the kinetic theory of matter. Anything that will give kinetic energy to the particles, right, will cause a change in state. That can cause a change in state. How? We will discuss that. But do you understand one thing? That in solids, the particles have less kinetic energy. In liquids, they have still more because they are going past each other. And in gases, it is the most because they are moving freely, right? So more energy you are providing to the particles, more chances of the particles for going from solid to liquid and then liquid to gases. Don't worry, we will discuss all this. There is a lot coming up. So yeah, but today I want to just give you the basics of it. Okay, this is the basis of the kinetic theory of matter. Heating a solid causes its particle to vibrate more. Of course, it's going to happen gradually. So let's say you have iron at a very low temperature and you start heating it. It won't immediately melt. First, the vibration are going to increase. So in a way, it is going to happen like that. So heating a solid causes particle to vibrate more. As the temperature increase, the particles vibrate so much that the solid expands until the structure breaks. This is when the solid melts into a liquid. So ultimately, the bond will start in a way breaking or getting very weak, and then it will become or start converting into the liquid state. Heating a liquid causes its particle to move more and ultimately spread out, completely detaching from each other, and then they convert into gases, right? Some particles at the surface gain sufficient energy to overcome the intermolecular forces. This is when a liquid starts to evaporate. So we will discuss that also, that how surface particles can acquire energy and then go into the gaseous state. So it is not the entire liquid, but only the surface particles going into the gaseous state. That is when we say the liquid is evaporating. So this is also we have to discuss. Today we are only introducing the concepts and then we will talk about each of them in detail. When the boiling point is reached, all of the particles gain enough energy to escape and the liquid boils into a gas. So are you understanding? Through kinetic particle theory, we are wanting to explain the conversion of solid to liquid and then liquid to gases, and always you can think vice versa. If you are taking out the energy from something, then gas will convert to liquid, and if you take more energy out of something, then liquid will convert to solid. So it can be both ways. It is a reversible thing. You can convert ice to water, but at the same time you can convert water to ice also. Of course you know that. Okay. If you want to write something, you can, but this is something that in the background we are already discussing. Okay, let's start with the next thing. So the change of state, of course, solid to liquid, liquid to gas. This is what I have explained. So it does not change the amount of matter. It does not change the mass. What it changes is the separation. So the separation changes. The intermolecular forces become weak, but the amount of matter does not change, of course, right? So heating and this is cooling, right? So this is what I was trying to show. Okay. Next, Brownian motion. So Robert Brown, 1827, observed, pollen grains in water, and he was observing it through a microscope. So those pollen grains were already detached from their parent plant, and of course they were like dead. And when Robert Brown observed them, he saw them moving randomly, like in this kind of fashion, right? So they were moving randomly from here to here, then here, in a way like this. So when he observed this, he was quite surprised. He was assuming that they were dead. Then how can anything move? So he tried to figure out like what exactly is happening. Then he realized that, since the water particles are not at complete rest, they are in motion, they can go past each other, and those particles, like the water molecules, they collide with these pollen particles, which can be called as microscopic. So pollen particles can be called microscopic, but they are not an atom, they are not a molecule. So the water molecules, they continuously collided with these and transferred their energy to the pollen particles, and in a way they were like moving. So when they were moving, so that gave him an impression that what are they alive, but it was not the case. He cross-checked that. So Brownian motion refers to the random movement of microscopic particles. What are these microscopic particles, students? So here, like the pollen grains. What else can it be? Smoke. So smoke can be an example of a microscopic particle. So smoke particle is not an atom, it's not a molecule, okay, in a fluid. So fluid, students, can be liquids or gases. What if I say fluid, that is in general liquids or gases. So even if we have smoke particles in the room, you will see them moving randomly, right? Why does that happen? Because of the air molecules. Now what is air majorly? Oxygen or nitrogen. They collide with those smoke particles and transfer their energy. So due to the collision by the molecules of the fluid, we can only see microscopic particles under the microscope, as the molecules are too small to be seen, of course. So examples of microscopic particles are pollen grains and smoke particles. All this you understand? So this was discovered by Robert Brown, and that is why this is called the Brownian motion. This has a very important role in the upcoming classes, but now you understand what is Brownian motion. So Brownian motion is basically the motion acquired by this random collision that keeps happening between a microscopic particles and the atoms or molecules of the fluid. Atoms or molecules of the fluid. Alright, students. So that is what we are trying to show, that it can only be observed through a microscope because these are very tiny particles. Alright, so you can copy this down, then we move forward, anything that you want. Otherwise, we will always try to share these slides with you in the description, and you can always refer to these slides, and I hope that all these things will help you during your exam. Alright, so let's talk about this. In which changes do the particles move further apart, right? So gas to liquid, what do you think? The particle gas to liquid, right, students? So it is in a way, what is happening? Cooling is happening and gas is being converted into liquid. So the particles are getting closer. Then liquid to solid. Let's discuss this, students. Why not? Gas to liquid. What do we call this? We call this condensation. We call this condensation. The conversion of gas to liquid is called condensation. All right. Then liquid to solid. What do you call that? you call it solidification. Solidification. Okay, so you don't need the definition here. Of course, you understand conversion of liquid to solid. When does that happen? When you take energy out of that liquid, right? There's another name for this, that is freezing. Of course, yes, that is freezing. Now, what about solid to liquid? So it has to be like melting. Solid to liquid has to be melting, isn't it? I hope you know that. And then liquid to gas, it is like boiling. So I'm not writing evaporation here. You might have learned again in your previous classes what is the difference between evaporation and boiling. In the next class, we will discuss that in detail too. But right now, you can understand that liquid to gaseous conversion is boiling. You can also call it as vaporization, right? Is there another scope? Is there a scope of gas to solid or solid to gas straight away? Can we bypass the liquid state? Yes, some material do that. For example, carbon dioxide, CO2, can straight away compressed and the gaseous form can be converted to solid, which we call as dry ice. Or menthol, or naphthalene, or camphor. There you can straight away convert solid to gas and gas to solid. What is that called? So if you ever convert solid to gas, okay, solid to gas, then that is called sublimation. That is called sublimation, okay. And gas to solid, this is called deposition, okay. Just for your general knowledge, that even there is a scope where the liquid state is not there. When does that happen? All this we will discuss in the next class, but I don't want you to burden you with that today, but just giving you the terms that are associated. So in which changes do the particles move further apart? So it is liquid, solid to liquid, that is Z, and liquid to gas, that is Y. So it should be Y and Z, isn't it? Because we are talking about where the particles will move further apart. All right. Diagrams X, Y and Z represent the three states of matter which change occurs during boiling. Of course, so this is solid, all are rigid, we can see they cannot move. In liquids, they are going past each other. So this is the solid state, this is the liquid state, and this is the gaseous state. So we are talking about boiling. So boiling is Y to Z, isn't it? So I hope I've done it correctly and there is no error. So liquid to gas, and that is like boiling. So that is Y to Z. All right, students. We'll discuss what is evaporation, how it is different from boiling, but not today, not in today's class. All right. Very quickly then, how do gases exert a pressure? So imagine, students, you will have air particles in your room. Are they at rest? Answer is no. They are continuously moving. They have kinetic energy. What is happening when, let's say, any particle is moving towards one of the walls? It collides, it returns back. Does it transfer a momentum or not? Imagine you have a ball in your hand and you throw it on the wall. Will it create a force on the wall or not? Of course, yes. So that force might be very small due to one ball. But imagine millions and billions of balls continuously striking the wall. The overall force will be ample. That is the idea of pressure, right? We will discuss that. What is atmospheric pressure? So every time we are also experiencing a pressure due to the atmosphere, due to the air, that is called the atmospheric pressure, right? So when the particles collide with the walls of the container, they exert a force on the wall. The force from one collision is small, but as there are many particles colliding all the time, the force exerted is going to be quite large. All right, students. So this is what I am trying to show, and we always assume that it's almost a collision in which no energy loss takes place, right? And so the particles don't continuously lose their energy on collision. Okay, this is what we are trying to show. The particles are colliding and transferring momentum to the walls. That is what causes the pressure. So now we have talked about temperature a lot. We have talked about volume a lot. But now we want to introduce a concept of pressure as well. Now, students, so pressure, volume and temperature. These are going to be the three heroes for the upcoming part, where we are going to discuss about gases, pressure, volume and temperature. Very quickly, students, pressure, you now understand what is that. volume is for a gas is something that they will acquire for the whole container. You change the container, you change the volume. So these are called you can call them as thermodynamic variables. These are the variables that are going to decide anything for the gas, and these three will define state of a gas. These three will define state of a gas. Students, we have talked about pressure in our previous unit as well. So let's talk about their units also. So the SI unit of pressure is Newton per meter square, which can also be written as Pascal. Volume, the SI unit is going to be meter cube. What about the temperature? This is what I want to discuss. So what is temperature now? Let's discuss that. We have used that word but never gone into the detail. So temperature tells you about the average kinetic energy of a particle in the system. Students, understand this. What does it tell you? Average kinetic energy. So compare summers and winters. So in summers you will say the average kinetic energy of the air molecule is way more. In winters the temperature is low, so the particles are less energetic, right? That is how you define temperature. So there is a concept of absolute zero. There is a concept of absolute zero. So absolute zero is a temperature where you would like to assume that it is such a low temperature that the particle's kinetic energy is almost zero. So that is why we call it as the absolute zero temperature. So for that we give the unit Kelvin. So 0 Kelvin means absolute zero. And let's not confuse it with 0 degree Celsius or 0 degree Fahrenheit. No, it is 0 Kelvin, the temperature at which all kind of motion would cease. So this is a very idealistic way of saying things, that at this temperature the particles will not have any energy, any kinetic energy. So that is why the SI unit of temperature is going to be Kelvin. All right. So that's about P, V and T, because now we are going to talk about how they are going to affect each other. So right now we were discussing solid, liquid and gas. Now we will remove solid and liquid apart and we will discuss about gases. And what are we going to discuss about gases? How these three will interplay with each other. All right. So, okay, how does the pressure of a gas vary with its temperature? So we are talking about pressure and temperature. So we are for time being we are not we are giving rest to the volume part. So we are not changing the volume because visualizing everything when all three are changing is going to be a little complex. So one by one we are going to see how one parameter affects the other. So we'll keep the third parameter aside. We'll assume that the third parameter is kept constant. So if we are discussing pressure and temperature, so we will assume that volume is being kept constant. And what better way of doing that? You keep the gas in a fixed container. The volume is not changing, there is no scope, but you have a burner and you can change the temperature. How will it change the pressure? So think about this. So this is what Gay-Lussac's law is. Okay, this is what we are discussing. Okay, so imagine if you provide more thermal energy to the particles, they will be more energetic. More energetic would mean what? That they are transferring more momentum to the walls. Imagine you throw the ball with lower speed and then you throw it with higher speed. How is going to affect the force? Of course, it is going to be more force if there is more momentum. So if you increase the temperature, definitely the pressure is going to increase as well. That is what we are trying to show. And when you achieve 0 Kelvin, then you might assume that almost the pressure is also going to be 0. So what do we have here? Pressure is directly proportional to temperature, or P1 over T1 is equals to P2 over T2 is what I have written for you. So that is what it is, that if you double the temperature, then the pressure will also double. But again, reminding you students, double the temperature means doubling it in Kelvin and not in degrees Celsius. Okay, so we will discuss how that is done, how to convert Kelvin into degrees Celsius in the upcoming class. Okay, but now you understand why pressure and temperature are like affecting each other. Of course you do. More temperature will always imply more pressure on the walls, provided volume is kept fixed. Okay. Next, students, very quickly then, how does the pressure of a gas vary with its volume? So what is that telling you now? So this is for the extended syllabus, but again students, you know, it's not always about the marks, it's also about the learning that you should have to understand things further. So there's no harm, even if you are from the core syllabus, you should be knowing all this. Okay, this is hardly anything, it will hardly take 2 minutes. Okay, so now what is being done? Temperature is being maintained. So we are not changing the temperature somehow, we are maintaining the temperature, and we are interplaying between pressure and volume. So you would say, how can you change the volume of a gas? The best way is through a piston. So this is a piston, so you can take it a syringe kind of a structure, and there is gas, and this gas, we have a pressure gauge which can measure the pressure, and if you suddenly decrease the volume, imagine what's going to happen. So if you decrease the volume, particles are still the same speed, but now they have lesser space to move. So collision with the walls will become more frequent, and if they will become more frequent, then that implies the pressure is going to increase. So are we saying that decreasing the volume increases the pressure? Yes. Vice versa, if we increase the volume, suddenly you move the piston out, you have more space. Same molecules, more space. So if they have more space, then they will collide with the walls less frequently, so lesser pressure. So can we say that pressure is inversely proportional to volume, or P1 V1 equals to P2 V2? That's Boyle's law for you. That's Boyle's law. How do we draw a graph for this, students? So it has to be a decreasing graph. You increase the volume, the pressure is going to decrease. That is how the graph would be. It won't be a linear graph, students. It won't be like this. Don't make a graph like this. Even that implies that on increasing volume, pressure decreases, but that is not true. Keep this graph in mind. This is very important. Ultimately, pressure will become zero when volume becomes infinite. So it can't be this graph. It is no linear relationship. Again, reminding you, this is very important. Okay. So I have written these points again for you. These are for the slides. So effect of temperature and pressure and on the volume of gas. So I have already talked about it. Still, I will read it out to you very quickly. So pressure is about the number of particles in a given volume. Increasing the pressure means that there are same number of particles but in smaller volume. Conversely, decreasing the pressure means that there are same number of particles but in a larger volume. So larger volume means less pressure, smaller volume means more pressure. So I won't waste your time on this. You can just visualize this by these two diagrams. More volume, more space, less pressure. Less volume, lesser space, more collision, more pressure. All right. So yeah. Next, how does the volume of a gas vary with its temperature now? So what are we doing now? Again, the same arrangement. We are talking about how to interplay between temperature and volume. So what is being kept constant this time? Pressure. This is called the Charle's law. All right. What do you expect? What is going to happen if you want to maintain the same pressure? Let's say this was the diagram and there is this piston. Okay. And what you are doing is, let's say here you have atmosphere. Okay. And this is free to move. This is free to move. Now imagine this, that you have a heat source here. So you are supplying heat, you are supplying energy. What is going to happen now? The particles here will acquire more energy. So when you supply heat, the temperature is going to increase. If temperature is going to increase, they will collide with the piston more and they will push the piston out. So if you imagine that, then temperature increases, the volume also increases, right? That is what we are trying to show. You increase the temperature means particles will be more energetic, they will push the piston out. So increasing the temperature will increase the volume. All right, students. So I think you can understand this is Charle's law. I have again made notes on this. So what are these? So increasing the temperature, increase the kinetic energy, all these things that I have already talked about. If the container walls are flexible and stretch, then the container will get bigger and bigger, just like the hot air balloon, right students? So if you keep heating the hot air in the balloon, you're not increasing the air, you're just heating it. Then also the balloon will start expanding, it will try to increase its volume. So when temperature increases, the volume of gas also is, right students? So now you know all the three, how they are correlated, and I think we can do some questions now. Okay, a gas cylinder holds 600 ml of a carbon dioxide at a pressure of this much, assuming the temperature remains constant. So what are we talking about? P1 V1 equals to P2 V2, isn't it students? Now, okay, so pressure was 2 into 10 to the power 7 earlier, now it has become 1 into 10 to the power 7. So what was the initial pressure? 2 into 10 to the power 7. What was the initial volume? 600 ml. Let's keep it in ml itself. The new pressure has become lower than the previous. So the new volume is of course going to be 1200 ml, right? So the pressure has become half, and that is why the volume has become double of the previous value. I hope easy and you should be able to understand. All right. Next one, a sample of a gas at a pressure of 1 into 10 to the power 5 Pascal has a volume of 100 centimeter cube. Determine the pressure of the gas when its volume is halved. All right, so volume is halved students, right? And so if the volume is halved, then the pressure is going to become double. So I'm not wasting time. So it's going to be 2 into 10 to the power 5 Pascal. Determine the pressure of the gas if the volume is reduced to 85. All right, so P1 V1 equals to P2 V2. Don't worry about the unit. You can give it a try yourself. So it was how much? 1 into 10 to the power 5. Volume was 100. Now the new pressure is what we have to find out. The new volume is 85, isn't it? So this is going to be 100 divided by 85. Let me do the calculation here for you. So 100 divided by 85, that's giving me 1.1. Okay, so the new pressure is going to become 1.17. So let's put it as 1.2 into 10 raised to the power 5 Pascal. So slightly decreasing the volume is slightly increasing the pressure. Determine the volume if the pressure is reduced to, so yeah, pressure is reduced, forgive me for this, is increased to, not reduced, it is the pressure is increased to 6 into 10 to the power, sorry, yeah, no, it's correct, because it is 6 into 10 raised to the power 4, yeah, it was 1 into 10 raised to the power 5, now it is 6 into 10 raised to the power 4, so power is 10 raised to the power 5, now it is 10 raised to the power 4, sorry. Okay, so again we will write P1 V1 equals to P2 V2. All right, so what was the initial pressure? Let me write it as 10 into 10 raised to the power 4. That will make things easy. Times 100 is equals to the new pressure, that is 6 into 10 to the power 4 into the new volume that we have to find out. So that's going to be 10 divided by 6 times 100, isn't it? So that is 167. So the new volume is going to become 167 centimeter cube. Right students? Easy. So now you've lowered the pressure, that is why the volume has increased. All right. Next. Okay. So that is what we are discussing now, the absolute zero, and then what happens at absolute zero in degrees Celsius, in Kelvin, the interconversion. So just to give you a fair idea of the temperature scales, because we need to know them before the next class. So let's just focus on this part first, that 0 Kelvin is not 0 degrees Celsius. That is why degree Celsius is a little awkward kind of a scale. Why? Because you would normally assume 0 degree, that means there is no temperature, there is no motion, but that's not true. Actually the 0 Kelvin would mean that. That is why we are now preferring Kelvin over degree Celsius. So 0 degree is actually the freezing point of water or melting point of ice in normal circumstances. So what is the difference between the two? So when it is 0 degree, it becomes 273 Kelvin, okay, 0.15 also. So every time you want to convert a temperature reading from Kelvin to degree Celsius, you should always use this, that temperature in Kelvin is going to be temperature in degree Celsius, which I am writing as theta, plus 273.15. This is very important, students. Okay. Why so? You can understand this is unitary method, because what is 0 degree is equivalent to 273.15 Kelvin. Imagine what is 1 degree. What is 1 degree? Then it is going to be 273. What is 1 degree? So you add 1. So it is going to be 274.15. For example, the normal human body temperature is 37 degrees Celsius. It is 37 degrees Celsius. How do you convert that into Kelvin? So in Kelvin, so let me write it as theta itself then. Okay. So in Kelvin, it is going to be 37 plus 273.15. You can ignore the 0.15 part also. So when you add 7, so this becomes 280 and this will become 310. So 310 Kelvin. So what is 37 degree is equivalent to 310 Kelvin. So you should keep this interconversion in mind, because many times the question would demand that. You would need the data in Kelvin and they would be giving the data in degree Celsius. So you should know how to do that, and vice versa would be temperature in degree Celsius is going to be temperature in Kelvin minus 273.15. Most of the times we ignore this 0.15 part and take it as 273. So know this, rest you can understand. You were more confident with the degree Celsius scale, which had 0 degree as the freezing point of water and 100 degree as the boiling point of water. And that is why there were 100 graduations in between, right, between 0 and 100. That is why this is also referred as degree centigrade. Centi means 100, right? But now you should be more confident with this one as well, 273 and 373. Okay, students, so you know this. Now you should also know this, and there is also Fahrenheit, that is 32 and 212. So these are regularly spaced. Here also you have 100 divisions between 273 and like freezing point and boiling point, but here it is more than 100. It is actually 180 divisions. But I don't want to burden you with this right now. You should just know degree Celsius and Kelvin. All right. Last two questions, students. First make a note of this, then we move forward. Okay, so put these three liquids in order of volatility, which with the most volatile first: water, ethanoic acid and ethanol. So who's going to boil first? Who will easily boil with a lower boiling point? So the boiling point for ethanol is 78 degrees. So it is most volatile. It can convert to vapor state quite easily. So least volatility is of course of ethanoic acid, right? Then it is going to be water, and then it is going to be ethanol. So the one with lowest boiling point will easily boil. We will discuss that. Why does that happen? How, you know, the boiling point changes for different liquids, but all that is not to be done today. It is going to happen in the next class. Table below shows the melting and boiling points of 4 substances. In which of these 4 substances are the particles arranged in a lattice at room temperature? I'll give you time, think about it. We want at room temperature. So let's say room temperature is 25 degrees Celsius. We want it to be solid. How? Because they are saying a regular structure, 25 degrees Celsius. We want it to be solid. So where do we see that? So melting point is 80 for B. For B, melting point is 80. So below 80, it is always in the solid state. While for this, the melting point is minus 115, minus 91, minus 23. So at 25 degrees Celsius, the melting point is already crossed. You understand what is melting point? The point at which the solid is going to melt, right? So only for B. So what can we write here? So B is going to be in the solid state. Why so? Why so? Because its melting point is 80. So it will start melting after 80 degrees Celsius. Okay, students, I hope your answer matches with mine. Last question then. Okay, all the substances have negative values for their melting points. Okay, which of them has the lowest melting point? Of course, it is going to be minus 182. Lowest melting point means the least value. So don't assume that 182 is a bigger number. I hope you know this much math. Minus 182 will be treated as the lowest number, lowest value, because whenever it's a minus value, then the bigger number is effectively the smaller value. That is why out of all the substances which has the lowest melting point, answer is going to be methane. Right, students? The next part, the melting point of the three substances are given in the table above. Which of the two substances are liquids at room temperature? Explain your answer. So what do we want now? We want the substance to be liquid. So it's let's say at room temperature, that is 25 degrees Celsius. So the melting point should be lower than 25. Okay, and the boiling point should be above 25. Then only you can expect that substance to be liquid. Okay, so lower than 25, that is the case. Higher than 25, that is the case. So ethanol classifies for that. Lower than 25, yes, but this is also lower than 25. So it will boil at 25 degree, it will boil. So methane will be in the state of gas at 25. Now again, mercury at minus 30 is its melting point. So below minus 30 it will be solid. Above 357 it will be gas, and in this range it will be liquid. So our answer would be ethanol and mercury. Why so? Because their melting point is like below 25 and boiling point is above 25. So I hope students you are able to understand whatever I discussed today. Boyle's law, Charles' law, Gay-Lussac's law, all these things. I hope you were able to understand the behavior of gases, solids, liquids, and the kinetic particle theory. So today was just the beginning of this unit of thermal physics. There is a lot to learn, and we will keep coming up with the videos very soon so that the momentum does not break and your studies will continue. And of course, as usual, then we'll come up with the previous year topical questions, which will ultimately tell you where you are, if you're able to do the questions well, and if not, then do let us know in the comments and we will try to come up with the solution. Right, students, if you're liking our work, again reminding you, please don't forget to like, share and subscribe to our channel. That really motivates us to keep working hard, to get up every day and work hard for you, and I hope you get the desired result ultimately with the help of our videos. Alright students, thank you so much for your time. I'll see you soon. Thank you so much. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.